Hi everyone, today we are going to talk about the law of sines. Before you continue on with this video, make sure you have the notes printed out and ready to go. Okay, so before we get started, I want to just remind you of when we first learned about the unit circle. We said when you have a circle centered at the origin, radius of 1, any point on that circle, I'll call that point P, has the coordinates of cosine of theta and sine of theta, if this is theta here. And we said that if we, the coordinates of that point are cosine theta, sine theta. If you were to dilate that point, so if you did a dilation of point P, right, then you would be moving that farther away. And we didn't talk much about dilations, but if you remember back to geometry, when you dilate something, you make it bigger, so it gets farther away from the origin or closer to the origin. And if we had a dilation of a scale factor of b, then all we would do is multiply each coordinate of that point by b. So, for example, if P was, this would normally be a radius of 1. So if P was 3 units away from the origin, then this would be 3 cosine theta, 3 sine theta. So that's the idea behind that. And that's actually going to help us out when we are determining the area formulas for a triangle. You have always done area formulas where you had a height and you had a base. However, in these cases, you are not necessarily going to have that. So how can you find the area if you're not given the height when you're normally used to finding the area of a triangle that way? So let's look at this first example. Here is y, here is x, here's my triangle. And remember that when you name a triangle, if we name our vertices with capital letters, our sides are named with lowercase letters, and the letter of the side corresponds to the angle that it is opposite from. So for example, here's angle B, so the side opposite would be here. This would be a lowercase b. Right, here's angle C, the side opposite is down here. This would be a lowercase c, and this would be a lowercase a. And so I've labeled all of the vertices and all of the sides. Now, if this angle here is my theta, then the coordinates of point C are going to just be b cosine theta, sine theta. And instead of calling it theta, let's go ahead and call that just a, because I have the vertex A there. So the coordinates of this point C is going to be this length B, b cosine A, b sine A. Okay, so that's the coordinates of that point. So if you think of the area of a triangle as 1/2 base times height, right now I don't necessarily, when looking at it, it doesn't look like I have a height. However, if I were to draw in this perpendicular here, and if I were to draw in that perpendicular, the coordinates of this point are coming from, right, this is a distance, and then this is a distance. If this was my height then is represented by that y coordinate, which is b sine A. And so I can say that my formula is going to be 1/2 my base, which is C, times my height, which is b sine A. And this might seem confusing. We're going to do the other two triangles, and then I think you'll see the pattern that's going on here. Okay, let's look at this second triangle. If this is A here, and this is B, and this is C. So this would be little a, this would be little c, and this would be little b. Now, once again, the height is on the outside of that triangle, right? My height would be here. That would be my height. So the coordinates of this point A, right, it's this distance. It's c units away from the origin, but the coordinates of that point are going to be c cosine of B times c c sine of B. C sine of B. And so when you're doing the area here, right, area of the triangle is going to be 1/2 your base times your height. In this case, your base is A. And your height, which is the y-coordinate of point A, would be C sine B. Okay, let's look at our last triangle. If this is C here, if this is A, and this is B, right? So this side would be little a, this side would be little b, this side would be little c. And in this case, your height is actually inside your triangle. And the coordinates of this point B are going to be A, because that's your distance from the origin, A times the cosine of angle C, that's the angle at the origin, times A sine of B, or excuse me, of C, A sine of C. And so the area of our triangle, 1/2 base times height, our area is going to be 1/2 our base, which is B, times our height, which is A sine of C. And so if you were to look at all of these formulas, notice the pattern that's going on here. It's 1/2 the two sides times the sine of the angle between them, right? So here's B. Let me do this here. So this is B, this is C, and A is the angle between them. In the second one, we've got 1/2. This is A. This right here is C, and B is the angle between them. Over here I have 1/2 B, which is this, times A, which is this, times the angle between them. And so that is our formula for the area of a triangle when you don't know the height. So what do you need to know? In order to find the area of a triangle, you need to know the measure of the two sides and the angle between them. As long as you have that information, you can use the formula to find the area of the triangle. So let's go through some examples so you can see how we're going to do this. And I would recommend that you always, always, always draw yourself a picture. So it says find the area of triangle ABC. So it doesn't really matter how you label it. I'll call this ABC. If C, little c is 8, little a is 6, and then this angle up here is 30 degrees. So I have two sides and the angle between them, so I can use that area formula. So my area formula is going to be 1/2 the two sides times the sine of the angle between them. And you can do all of this in your calculator. Sine of 30 is 1/2, in case you forgot that, but you can do this all in your calculator. Now, when you use your calculator, make sure when you do these that you are in the proper mode, that you are in degrees, otherwise you're going to get the wrong answer. Okay, so we're going to go ahead and do that. If we did 0.5 times 8 times 6 times 0.5, the reason being sine of 30 is 1/2, and I can just do that this way. Sine of 30, just put it all in your calculator, and you end up with an answer of 12. And we'll just put u squared for unit squared. Same idea with this one. I've got the area of triangle ABC, or excuse me, ABD, and I clearly didn't draw it to scale, but it's just a visual to help you to see that you have two sides and the angle between them. So in this case, if AB is actually let me redraw that triangle, because I do want to make a point here. If you look at the measurements they give you, they're telling you that angle DAB is obtuse. And again, it doesn't really matter if you draw it correctly. I just want to show you guys what's going on here. So DAB, if this angle is 150, and I know AB is 8, and I know AD is 6, so I have two sides and the angle between them. So if I find the area of that, I'm going to have 1/2 8 times 6 times the sine of 150. So if you don't see it already, that's okay, because you can do this all in your calculator. However, the sine of 30 and the sine of 150 are the same thing, right? Because those angles add up to 180, and sine is positive in the first and second quadrant. Sine of 30 is 1/2, and the sine of 150 is also going to be 1/2. Everything else here is the same, so this is also going to be 12 units squared. So you could have two very different looking triangles that actually have the same area. Okay, I'm going to stop this video. Please continue on to the next video for the rest of the notes. All right, thanks folks.